screen is far away and
Welcome.
small.
Today on Dr. Dutch, we'll be launching a rocket into space. Don't worry, it's not like it's rocket science.
By the end of this episode, you will understand one-dimensional kinematics and be able to analyze the motions of projectiles. We will analyze the changing velocity and constant acceleration on the rocket. We will use the rocket's time of flight to calculate the velocity and its maximum height.
Our whole universe was in a hot, dense state that nearly 14 billion years ago expansion started. Wait, the earth began to cool, the autotrophs began to drool, Neanderthals developed tools, we built a wall. We built the pyramids, math, science, history, unraveling the mystery that all started with a big bang.
Now here's my assistant to show you what you need.
Alright, so for this lab, you need a meter stick, a rocket, an air pump, a valve, a timer, safety goggles, and a sounding test to help you do what.
Safety procedure. Always remember to wear goggles. When you're pumping the rocket, don't lean over it. Watch out for other groups, and don't try to catch the rocket.
Thanks, Steve. Now that we've got that out of the way, let's move to the more exciting part. Once you have all your materials, you can start setting up the rocket. First, you're going to put on the valve. Next, you're going to put the rocket on. Make sure you press down on it so that the valve's secure. Then you're going to put the top of the rocket on. Next, you're going to attach the pump. Make sure you lock it by opening up the valve. Now you're ready to launch. Make sure you have safety goggles on and the air is clear.
Way to go!
In order to calculate the average total time for each valve, we have to add up each of the times for that valve and divide it by the number of trials. So we set up the equation. The average total time is equal to T1 plus T2 plus T3, all divided by 3. Now we plug in our values and repeat this process for each valve. In a free-fall problem, the time up is equal to the time down. This means that in order to find the time up, we can take the average total time and divide it by 2. So we set up the equation, T up equals average total time divided by 2. then plug in each of our values for the low, medium, and high valves. To find the initial velocity of the rocket, we're going to use the equation v equals v0 plus at. Since it's a free fall problem, acceleration remains constant at negative 9.8 meters per second squared. Then we will plug in the calculations from each valve and repeat this process. At any given height in a free fall problem, the velocity up and the velocity down have equal magnitudes but opposite directions. So to find the final velocity, we will set up the equation v equals negative v0. And then we will plug in the values from each of the valves and repeat this 3 times. In order to find the maximum height of the rocket, we will use the equation d equals 1/2 at squared plus v0 t. Since it's a free fall problem, acceleration is constant at negative 9.8 meters per second squared. In addition, since if it hits the maximum height at the apex, we will only be using the time up. So we will plug in the values and repeat this for each of the valves. For our calculations based on frame-by-frame pictures, the time for each frame was 1/30th of a second. Starting with the low trials, we looked at the videos to examine the distance that the rocket covered within one frame. This is how we got the values of d1, 2, and 3. Then in order to calculate the average distance it traveled within one frame, we set up the equation that the average d equals d1 plus d2 plus d3 all divided by 3. Then after we plugged in, we got the values. For the low trials, this was 0.71 meters, and then repeat the whole process for the medium and the high, which we got 0.8 meters and 0.92 meters. We then used these results in order to find the initial velocities of the rocket. For the low, we used the average distance it covers in one frame, and then we used the equation average velocity equals distance over time, so the distance was the average distance we found previously, and then the time was 1/30th of a second for the frame. And then we performed this calculation for the low, medium, and high trials, and we got 21.3 meters per second, 24 meters per second, and 27.6 meters per second. Since the rocket is an object in freefall, the acceleration always remains constant at negative 9.8 meters per second squared.
As we changed the valve from low to medium to high, the absolute value for all our calculations increased. From low to medium, the average time increased by 1.5 seconds. From medium to high, it increased another 0.9 seconds. This makes sense because a higher initial velocity means it will take more time for the rocket to slow down to 0 meters per second and begin descending. Once the rocket is launched, it experiences an acceleration of 9.8 meters per second squared towards the center of the Earth. Now for the initial velocities. As we change the valve from low to medium, the initial velocity increased by 7.5 meters per second. From medium to high, it increased by 4 meters per second. This makes sense because as the valves increase the pressure in the rocket, it should launch at a quicker speed. As the initial velocities increased, the final velocities did as well. This makes sense because the final velocity is the same magnitude as the initial velocity with an opposite y direction. For example, if the initial velocity of the rocket was 30 meters per second, the final velocity would be negative 30 meters per second. The velocity and max heights increase proportionally with time because they're dependent on time through the equations Vf equals Vi plus At and d equals 1/2 At squared plus Vit. We compared the velocity found using the frame-by-frame method with the velocity found using time equations, and the results were a little bit off. This can be accounted for by human error timing the rocket as well as air resistance.
In addition, the motion of the rocket can also be displayed by the graph shown. As it was shot upward, it has an increasing displacement from the surface of the Earth, causing the y position value to increase. But as it ascended, it also had a positive velocity that was decreasing, which accounts for the parabolic shape of the displacement curve. The displacement does not increase at a constant rate, so as it rises, it covers less distance each second. Once it reaches its apex, the vertical velocity is 0 as shown by the line's intersection with the x-axis. This is also the point when the rocket was at its highest point, as shown by the vertex of the parabola for the displacement. Then, on the way back down, the rocket's displacement from the Earth decreased, displayed by that curve heading back down towards the x-axis. The direction of the velocity on the way down is negative, which is why that straight line extends beneath the x-axis. Finally, since this projectile is in free fall, it has a constant acceleration of negative 9.8 meters per second squared, as shown by its horizontal line below the x-axis. It is also important to note that when measuring altitude based on the frame-by-frame pictures, we consistently measured from the ground to the bottom of the rocket.
I messed up. I don't want it to coming out of the wrong
Go.
She's running out of storage. Oh, okay.
Go.
Next you.
Go.
Now you.
Go. Go.
Always remember to use safety goggles.
Bro, no intro. What the hell?
Alright, so for this lab, you need a minute. Oh, wait.
Where'd it go?